Today, the first ever experiment that showed that angular momentum was quantized. Let's go. So far, we've discussed two major themes about quantum mechanics. The first is H, Planck's constant, the thing that sets the finite resolution for the information carrying capacity of space and time. In particular, we've studied how H quantizes angular momentum into integral units of the value h over 4 pi. We've also learned that angular momentum is not only quantized in its values, but it's also quantized in its observations. So if we think of it like a vector, any projection of that vector along a specific direction, like the x component of the angular momentum vector, will also be observed only in integral units of h over 4 pi. We've also learned to distinguish between two different kinds of angular momentum, spin and orbital. Orbital angular momentum, you might recall, is something that an electron has as it orbits a proton in a hydrogen atom, or something that a functional group of a molecule might have as it orbits around its molecular axis. Somewhat more confusingly, you can also think of a linear molecule like carbon dioxide, which will orbit around its own center of mass. To tell the difference between orbital angular momentum and spin angular momentum, it helps to recall that particles are born with a very specific kind of spin angular momentum. It's part of their definition. And anything beyond that, anything that can change, speed up or slow down, if you like, is orbital angular momentum. Now, just because we can observe angular momentum only in specific directions, just because the angle at which we can observe that vector is restricted to integral units, doesn't mean that those are the only values that a spinning molecule or atom can take. The angular momentum of a given particle can be, in principle, pointed in any direction. It's just that we can only observe them in those quantized values. So what happens then when the angular momentum vector of a given particle is found to be in between two of the observable options? What happens is nature chooses one of those two options at random. And this brings us to our second major theme of quantum mechanics that we've been discussing, and that is probability. Nature can only answer questions probabilistically. What keeps quantum mechanics then a scientific enterprise is that we can actually compute from first principles those probabilities with precision. We can, in other words, make precise predictions for what we expect to see and then run an experiment to verify it. Over the next few episodes, we are going to build towards doing precisely that. Today, we are going to explore what is probably the easiest of those kinds of predictions to make. We're going to explore the case of a silver atom, which has the smallest non-zero value of spin angular momentum allowed, h over 4 pi. Now, naively, these two themes of quantum mechanics tend to conflict. They tend to contradict each other. I can hear it already. In fact, I get the emails all the time. Hey, Sean, doesn't the probabilistic features of quantum mechanics mean that the universe can and does carry information, that angular momentum that can in principle point in any direction? Isn't it just that we can't access that information? Doesn't the universe actually know what the correct angle is? What a question. It's a great question, and getting to the answer of this question will get us to the heart of understanding quantum mechanics. But unfortunately, that answer is a little tricky because that question actually is not well defined. It contradicts itself in the wording of the question. It's more of a koan than an actual scientific question, something to meditate on. For a more extreme example, consider the following koan. What is the information content of a disk that you can never access? Let me put it bluntly. The answer to any scientific question will always be done via experiment. Experiments literally create information. And what quantum mechanics tells us is that While we cannot predict precisely what will happen, we can predict what the options are, and we can predict what the relative probabilities of all those different options are. And so the content of our prediction, if you like, amounts to specifying what can happen and what the probability of each of those options are. And we can do experiments to verify that this is in fact the case. In other words, there is some intrinsic noise, some statistical fuzziness associated to nature. And that's what we mean by nature having a finite resolution for its information carrying capacity. This is what we mean by H. We will come back to this apparent conflict, this koan, in due course. But for now, let's visit the very first experiment that verified the existence of H, this finite resolution for information, using the spin angular momentum of silver atoms. That is the Stern-Gerlach experiment. For today, we are going to study the test case of a silver atom. We are going to learn how to build an experiment to specifically confirm that a silver atom has spin angular momentum h over 4 pi and is subject to the rules of quantum mechanics. To do that, we first need to learn how to manipulate the spin angular momentum of a silver atom. And to do that, we need to talk about magnetic fields. We've talked about it a lot, right? Moving electric charges generate magnetic fields. So in particular, spinning electric charges, like electrons and protons, can generate their own dipole magnetic fields. Along the axis of that magnetic field is aligned perfectly with its spin. Uncharged particles can sometimes also have a magnetic field, a dipole magnetic field, and this happens when those uncharged particles, like the neutron, are composed of smaller particles that do have electric charges. So for the neutron's case, it's got 2 down quarks with minus 1/3 e and 1 up quark with plus 2/3 e. Similarly, a silver atom will have a bunch of protons in its nucleus that give an electric charge, a positive electric charge, and a bunch of electrons orbiting around that nucleus, giving it a net 0 electric charge. The silver atom is exceptionally special in the sense that it has one outermost electron in its 5s orbital. And so essentially, all of the spin angular momentum, the net spin angular momentum of the silver atom, is basically comprised of that small spin angular momentum of that outermost 5s electron, which happens to be h over 4 pi. And this is nice because it's much easier to work with an electrically neutral particle like silver, because then you don't have to worry about interference effects from electric fields and causing the particle to bounce around. What the silver atom does for us is it effectively shields that electric force completely off by Gauss's law, right? And all we're left with is a slightly longer range magnetic dipole field that is aligned with the spin of the silver atom. Quantum mechanics predicts that particles with a spin angular momentum of h over 4 pi, particles like silver atoms, have only 2 observable values of angular momentum in any direction, that is, h over 4 pi and minus h over 4 pi. In terms of angles with respect to which that spin angular momentum vector is pointing, we can either measure it at 0 degrees or 180 degrees. The Stern-Gerlach experiment is the original experiment meant to verify that this is the case. And it is made up of 3 separate components: the beam of silver atoms, a big honking magnet meant to differentially impact the velocities of those silver atoms in the beam, and finally a screen with which we can use to detect which way the silver atoms went. If quantum mechanics is correct, then we can only observe 2 angles for that spin angular momentum in any given direction, 0 and 180 degrees, with respect to the detector. And so what we would see in terms of the Stern-Gerlach experiment is that beam of silver atoms would be split in 2, up and down. If quantum mechanics were not correct and we were able to measure any angle of spin angular momentum with respect to the magnet, then what would happen instead is that beam of silver atoms would be smeared differentially depending upon the angle at which that spin angular momentum makes with the orientation of the magnet in the detector itself. In other words, the experiment was looking for a split of the beam versus a smear of the beam. To better understand how all of this works, let's look at each of those components separately. The beam of silver atoms was created with some ingenuity. They took a big metal box and put a lump of silver inside and exposed that lump of silver to some heat. That heat caused the individual atoms in the lump of silver to sublimate off, to break off from the crystal structure and start to float around the box. Now, if you poke a pinhole in one side of the box, what will eventually happen is all of those silver atoms that are floating around randomly in the box will eventually make their way to the pinhole. Maybe not all of them, but a good chunk of them will make their way to the pinhole and fly out like a spray, like a nozzle of silver atoms that comes out of one side of the box. In order to focus that spray of silver atoms, what you can do is slightly downstream from that spray, you put another screen, another wall, if you like, and poke another pinhole through that screen, which would therefore block any of the other spray of silver atoms except for the ones along a linear beam line. And so it's kind of a cheap and dirty, quick and dirty way to make a beam of silver atoms, but it's very effective. One important thing to keep in mind here is that because the silver is sublimating off of that lump, thermally, if you like, their kind of angular momentums are pointing in any which direction, and they're not necessarily correlated with which way the beam is going. So, in other words, the spins coming out of the oven through the screen along the beam line, they are all moving to one side, but their spins are pointed randomly in all different possible directions. Last time we learned that the spin angular momentum of a particle is related to its magnetic dipole moment. And this is great because it gives us an opportunity to influence particles that are electrically neutral but happen to have a non-zero magnetic dipole moment, like the neutron or a silver atom. We can influence the direction of a silver atom's magnetic dipole moment or its spin, remember they're exactly aligned, by applying an external magnetic field. When we apply an external magnetic field, the spins of the silver atoms want to align themselves with that magnetic field. In some sense, there's a torque, and that torque is equal to the magnetic moment parameter, that mu vector, crossed with the direction of the magnetic field, that b vector. Alternatively, we can reinterpret this torque as a potential energy, and that potential energy is minimized when the angle between the magnetic dipole moment and the applied external magnetic field is equal to zero. That is to say, when they are precisely aligned. Now, as it turns out, that torque formula is only valid when the applied external magnetic field is precisely constant. But the potential energy formula is actually generically true for any arbitrarily shaped magnetic field. In what follows, we're going to use this fact and construct a magnetic field that has kind of a complicated shape. From elementary physics, you might recall that a potential energy is related to a conservative force in the sense that the conservative force is the gradient or directional derivative of that potential energy function. What that means for us is that if we apply a magnetic field that varies in space, then the silver atoms, the magnetic moments that experience that magnetic field, will experience a force along that variation. So Stern and Gerlach basically took a magnet with a sharply pointed end to create a magnetic field with a large gradient and exposed the beam of silver atoms to that magnet aligned in, say, the x direction. For our purposes, the derivative dB by dx doesn't really matter that much. All that matters is that it's large, and we can do that by having a sharply pointed magnet. What this means is that that sharply pointed magnet will give a kick to the silver atoms passing near it, and that kick will be directed along the angle relative to the detector of the spin of the silver atom. In other words, the silver atoms will be migrating along the beam, along their merry path until they run into the magnet. Once they run into that magnet, they will be deflected. They will experience a force proportional to the cosine of the angle between their spin and the detector. In other words, the magnetic field will distort the beam differentially depending upon the angle. And of course, quantum mechanics says that we can only measure two specific angles. Finally, let's talk about the detector screen. So the detector screen is just basically some screen, some sheet, some wall in which the silver atoms will eventually be deposited onto. So if quantum mechanics were correct, the deflected silver atom beam that split in two would lead to two distinct clumps of silver atom, one above the magnet, one below the magnet, right? For up and down, respectively. If quantum mechanics were not correct and the angle at which those particles were spinning could be continuously observable, then what we'd see instead is that beam would have been smeared out over the entire detector screen. So qualitatively, one prediction of quantum mechanics is that in the middle of that screen, there should be nothing. There should be no silver atoms. Of course, what was observed is in fact that the beam split in two. There was a clump of spin up silver atoms at the top and a clump of spin down silver atoms at the bottom. If you were to find a way to repeat this kind of experiment with a spinning object that had spin of h over 2 pi, then there would be three available angles for you, and what you would find is three separate lumps, one for h over 2 pi, one for 0, and one for minus h over 2 pi. Similarly, if you were able to do this with an object that had spin angular momentum of 3h over 4 pi, then you would see four separate angles corresponding to four separate lumps on the screen. What separates kind of particles that are influenced by quantum mechanics because they're so small, like silver atoms, from everyday classically experienced objects like, I don't know, balls, like baseballs, is that those really large objects have the capacity to hold an enormous amount of angular momentum, right? And so what we are actually observing there is a spectrum of tiny little differences between options that is so fine, in fact, that it's probably finer than the resolving capabilities of any experiment that we could ever hope to build. In other words, it has way too many options. So in some sense, the distinction between classical physics and quantum physics is that quantum physics, you start to worry about things that are small enough so that the finite resolution of the information carrying capacity of space and time is important. The actual physical results of this experiment that occurred are a little messy, but they're definitely worth taking a look at. So I'm going to flash for you a postcard that the two experimenters, Otto Stern and Walter Gerlach, sent to Niels Bohr, one of the leading figures in the development of quantum mechanics at the time, with their experimental results baked onto it. So what we can see is for the case of no magnetic field turned on, it's just a line, the beam went straight through. And when they turned the magnetic field on, we see that that line got deflected, got split into an oval-like shape. So why is it an oval-like shape instead of a pair of dots? Well, let's dig into it. So first of all, why is there any thickness at all? Well, of course, there's going to be some experimental error when designing the beam, right? So we have to poke a hole in the oven. That hole is going to have some thickness, and that thickness is going to be wider than the thickness of a silver atom because we want some silver atoms to come out. Moreover, the hole in the secondary screen used to create the beam will also have some thickness, and there's going to be some experimental error in making sure that those two holes are of the same thickness and are precisely aligned. Sum total of all of those things means that that beam is going to have a certain thickness to it. And the atoms in the silver atoms in the beam, some will be in the middle, probably most of them will be closer to the middle, but some will be off to the sides along that beam differentially. Right? So the thickness of that oval that you see on the postcard is related to the thickness of the beam in this sense. Now, additionally, the super sharp magnetic field is going to act differentially, kick those silver atoms differentially, depending upon how far away they are from where that sharp point is. So for atoms in the middle of the beamline, they're going to get a bigger kick than atoms that are slightly off the center of that beamline, which is why we see on the postcard at the widest, in the middle, in some sense, the oval is at its widest. And as you start to get kind of further away from the middle, the kicks become smaller and smaller and smaller, so that it kind of closes out to form more of an oval shape. And eventually the kicks become negligible with respect to the error in the beamline, which is why those two black lines eventually flatten out and meet each other, forming that oval. This is just how experiments normally operate. What's important here is that you can definitely see that in the middle of the beamline there was a definitive split between the up deflected atoms and the down deflected atoms. If quantum mechanics were not correct, what we would have seen instead is that beam would have been smeared, and so instead of an oval shape, you would have found a completely smeared out blob. In other words, that oval shape would be completely filled with silver atoms. Neat, huh? But that postcard, by the way, sits in the Niels Bohr archives in Copenhagen. Today, we've considered the quantum effects of a bunch of randomly spinning silver atoms directed along a beam. Next time, we are going to tweak the initial conditions to be a little bit more precise and just add one small layer of complexity, again, onto this experiment. Thank you so much for watching. See you then.